You can also have triple bonds. Okay, an example of a triple bond would be like 4 nitrogen. Nitrogen, 2 nitrogens would give me 10 valence electrons. So what happens here? Put them side by side, pair to bond, 4, 6, 8, 10. So see how there I need both nitrogens to have. So I'm going to bring in 2 lone pairs. Oops, let's try that again. And now I've still only used 10 electrons, but now each nitrogen has 8 valence electrons around it. Okay, polyatomic ions. Polyatomic ions, all right, in the previous unit we looked at how ionic substances, for example, let's look at sodium carbonate. Okay, remember how that dissociates in water to where I would get 2 sodiums and 1 carbonate. Okay, so characteristic of an ionic substance is it breaks apart or dissociates in water. But remember, you did not break apart the carbon and the oxygen here, and that's because the carbon and oxygen, they are covalently bonded to each other to make this carbonate polyatomic ion. Covalent bonds do not dissociate in water. So we can use Lewis structures to model polyatomic ions. And the procedure is the same. There's just an initial step that you have to do extra, and then an ending step that you do extra because this is an ion. So let's just look at carbonate. Okay, so we're going to go through the same process. 1 carbon, 3 oxygens. So that would give me 22. Now, because this is an ion, I have to account for that charge. The way I do that is if it's negative, I'm going to add the electrons to my total. If it's positive, I'm going to subtract the electrons from the total. So this is a -2, so I have 24 electrons to work with. So same process. Bond them with pairs, 8, 10, 12, 14, 16, 18, 20, 22, 24. And now I need to move 1 pair in so that my carbon gets that. And then at the end, I want to distinguish this as being an ion. So I'm going to put brackets around my Lewis structure and then put the charge on the outside. Okay, let's look at a positive one here. How about ammonium? Okay, I would have 1 nitrogen, and I have 4 hydrogens. That gives me 9. And then because I have a positive charge here, I'm going to subtract an electron from that. So I'm going to have 8 electrons to work with. Nitrogen will be in the center. Okay, and I'm going to bond each to there. And nitrogen has 8, hydrogen has 2, and I've only used 8 electrons. So the structure is good. And we're going to put brackets and a +1 to finish it up. Okay, resonance structures. We had an instance in the carbonate that we did before. Let me just switch back to that real quick. And where I needed to put a double bond in. And so I put it over here. But I could have chosen this oxygen up here to pull it from. I could have chosen this oxygen here to double bond to. They would all be equivalent, it's just the location of the double bond would be different. Okay, there's a special thing that occurs when that happens. Alright, we're going to look here at ozone, O3. And when we do that Lewis structure, we also see that we need a double bond. Well, with ozone, I could have done a double bond on the side that's shown here. could have drawn a double bond on the other. Okay? But when we observe it in nature, it doesn't exist with two different size bonds. What we actually see is that the bonds are equivalent. Okay? And so, again, these Lewis structures are all about giving us some kind of an idea of how this thing exists in nature. And so we want our drawing to reflect that. So what we do in the case where we have these resonance structures, these are structures that are equivalent. In this case of ozone, I could have put the double bond on either side. And so the correct way that we draw that is you just draw both versions and put a double-headed arrow in between them. Okay? And again, the key thing to remember about that, even though resonance we think of oscillating things, is that really that's not what is happening. We're not going to go very much into what actually is happening, but just be aware that it's forming two bonds that are equivalent to each other, rather than a pure single bond and a pure double bond. We know that from observation. And we also know it's not just, the double bond is not like switching back and forth between the two either. It's a formation of this equivalent bond that is somewhere in between a pure single bond and a pure double bond. Okay, there are some exceptions to the octet rule. The first type we'll look at is where we have atoms that have less than a full octet, and that is the way that they exist. I call these wimpy atoms. These are atoms that basically will not force another atom, especially those with high electronegativity, to share electrons with them. And so what you'll see is that for this example here, we have boron trifluoride. And when you draw the Lewis structure for that, you end up where you don't have enough pairs to give everything 8. But boron, being the wimp that it is, will not force fluorine to share another pair of electrons. And so it's happy with 6. All right. Other common atoms that you'll see that do this, beryllium and aluminum. So those are the 3 ones that you just need to be aware of, is that when you have these, especially bonded to halogens, they won't force a double bond to be formed so that they can have their 8 valence, or their 8 electrons. Another case is that some can have greater than an octet. And so the key thing about this is that our center atom must have access to a d sublevel. So it has to have electrons in at least the 3rd energy level so that it can use that d sublevel to bond. And there are two cases that you'll see this. One is where you have more than 4 atoms on this around the central atom. And so phosphorus pentachloride, we would end up, and we would kind of draw this, where we sort of just position them around and bond them this way. And then kind of just fill it in there, okay? So that's one case that you may run into. The other is one like triiodide. This is a polyatomic ion. And so we have 3 iodines, that's 21, plus the 1 for the charge. So I have 22 electrons to work with on this. And I bond with 2 pairs, 10, 12, 14, wait, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And what happens here is I have an extra set of electrons available. So I'm going to put that extra pair on the center. So the center atom will get any extra lone pairs that there are.